All right, so what are we doing? We are taking a map of extreme water levels at the coast derived from hydrodynamic models and constructing maps of overland inundation depth and extent. We're doing this at high resolution over a large area for multiple water level scenarios, which means several terabytes of data processing. So the approach, we use a bathtub inundation model, which simply means taking the difference between the water levels and the land elevations to determine the flooded areas. However, we incorporate two adjustments. One, hydraulic connectivity, meaning that for a pixel to be flooded, it has to be connected by a pathway of flooded pixels all the way to the coast. And two, attenuation, which refers to the natural reduction in water depths as the storm tides move inland. And this results in less overestimation of flood depth and extent than a simple bathtub model. And the work is inspired by the methods developed in Kasmalkar and others, 2024. So how can we implement the path-based model as efficiently as possible? Let's use some basic Python. I imagine most people who code in Python are familiar with this import statement. But have you seen this one? Cupy is like numpy, but it runs on the GPU instead of the CPU, so it can do the calculations faster. It mimics the numpy array class, which means that if we can restrict all the stuff we want to do to simple numpy array manipulations, we can speed up the model. We can substitute cupy for numpy one for one. All right, so what are the model inputs? The data we need to implement the model include the following: an array containing our topography, an array containing the water levels at the coastline, which we then interpolate inland, and a rasterized mask of the coastline so our model knows where to start. The first thing we need to do is calculate the bathtub inundation levels by taking the interpolated storm tides, subtracting the topography, which gives us the bathtub inundation depths. Now we start the path-based model. We identify land pixels at the coastline in the bathtub inundation array. At those pixels, we set a distance counter array to keep track of our current distance from the coastline. Then we fill our path-based inundation array with water levels adjusted for attenuation, meaning we take the bathtub water levels, subtract some attenuation based on how far we are from the coast. Since we're at the coast in iteration 0, attenuation is 0, our water depths are the same as in the bathtub model. Next, we identify neighbors of flooded pixels. We select the newly inundated pixels, shift the array one to the right, one to the left, and so forth, to identify neighboring pixels which have not been considered previously. We update the distance from the coast at those newly identified neighbors. Next iteration. Now, considering these newly flooded pixels, we do the same thing again, finding them in the bathtub inundation array, setting the path-based inundation array to the bathtub water levels minus attenuation, which we do have in this case. We select those newly inundated pixels, find their neighbors not previously considered, and calculate the distance from the coast for those new neighbors. We keep iterating until the water stops, which in this toy example is after iteration 2, but with the real data was often more than 1,000. So in summary, the workflow enabled more realistic inundation mapping than the simple bathtub model, efficient computation over a large extent, processing of multiple water level scenarios, self-documenting and reproducible methodology, and all of this was done in a simple Python environment with minimal dependencies. Thank you.